In this video, I'll be discussing Hess's law. Hess's law states that the enthalpy of an overall reaction is equal to the sum of the manipulated reaction enthalpies for each individual step of the reaction mechanism. And even though I specify enthalpy here, you could also apply this to entropy. Essentially, you're going to have an overall reaction that is generated by a series of reaction steps called your reaction mechanism. And each of those reaction steps has its own enthalpy of reaction. And you're going to manipulate those reaction enthalpies for each of your steps, add them up, and that will give you the overall enthalpy of reaction for your overall reaction. And there's two ways you can manipulate your enthalpy values. If you have to reverse one of your reaction steps, you're going to flip the sign of your enthalpy value. So for example, if you have a reaction step that has a negative enthalpy and you reverse that reaction step, you would flip the negative to a positive enthalpy value. And if you have to multiply a reaction step by a constant, you would multiply the enthalpy value by that same constant. So for example, if one of your reaction steps has to be multiplied by 2, you would multiply the enthalpy value for that reaction by 2. And then at the end, you just add all of them up, and that would give you the overall enthalpy of reaction. So let's look at this example down here. So in our overall reaction, we have solid carbon plus hydrogen gas producing propane gas. And we have a series of 3 reaction steps that make that. And what we need to do is we need to figure out how we're manipulating each of these enthalpy values to get the overall enthalpy. So what I like to do when I approach these Hess's law problems is I like to keep my eyes on the prize, so to speak. So I'm always going to keep in mind what this overall reaction is looking like, because I want to judge each of my individual reaction steps by the overall reaction. For one thing, I want to know what side of the arrow certain compounds are on. For example, is something on the product side or is something on the reactant side? And I also want to keep track of how much of each compound I have, because each of those things is going to tell me how I'm going to manipulate each of those reaction steps. So let's just start with the first step up here. In our overall reaction, you see we have propane gas on the product side. Whereas up here in this first reaction step, I have propane gas on the reactant side. That means I'm going to need to reverse this first step. And that's because I need to get that propane gas on the product side. So if I reverse this step, that would get me there. And we know that if we reverse a reaction, we need to flip the sign of the enthalpy value. So here, the enthalpy value was negative, but since we reversed the reaction, we're going to change that negative into a positive. Next, we have the second step here. And I see solid carbon here, and it's on the reactant side. In my overall reaction, I have solid carbon on the reactant side. So we don't need to flip this second step, but in my overall reaction, I have 3 of those solid carbons, whereas up here I only have 1. So I'm going to go ahead and multiply this reaction step by 3, and that will get me the 3 carbons that I need. So if I multiply the step by 3, I also need to multiply the enthalpy value by 3. So down here in my third step, I see I've got hydrogen gas on the reactant side, and in the overall reaction I have hydrogen gas on the reactant side. But in the overall reaction I have 4 hydrogen gases. Up here I only have 1, so I'm going to go ahead and multiply this step by 4. And that will get me the hydrogen gases that I need. So I also need to multiply the enthalpy value by 4. So let's go ahead and take a look at what this looks like after we've done all of these manipulations. Let's see what our mechanism looks like then. So this is the reaction mechanism after all the manipulations have been taken into account. So for the first step, we needed propane gas on the product side, so we reversed the reaction. And because we reversed the reaction, we flipped the sign of our enthalpy value from negative to positive. For the second step, we didn't reverse anything, but we did multiply everything by 3. Therefore, we multiplied the enthalpy value by 3. And for the third step, we didn't reverse anything, but we multiplied everything by 4. So we multiplied the enthalpy value by 4. And you can see that there are compounds in the mechanism that don't show up in the overall reaction. And just to show you how they cancel, that's an easy way to check and make sure your manipulations are correct in your mechanism. If your manipulations are correct, all the intermediates should cancel and you end up with your overall reaction. So we have 3 intermediates here: carbon dioxide, oxygen gas, and water. And each of those should cancel after we've done our manipulations. So you can see up here we have 5 oxygen up here on the product side, and over here, after we multiplied everything by 3, we get 3 here, and after we multiplied everything here by 4, we get 2 here. So we got 5, and 3 plus 2 is 5. So the oxygens cancel. We have 3 carbon dioxides up here, 3 down here, so they cancel. We have 4 water here, and 4 water here, so they cancel. So you're left with your propane, your 3 carbon solids, and your 4 hydrogen gas molecules. And that's what's in your overall reaction. And that's, like I said, a quick way to check to see if your manipulations were done correctly. So now that we have all of our manipulated enthalpy values, we can go ahead and add them up to get our overall enthalpy. So you'll just take each step and add them together. And once you add them all together, you should get your overall enthalpy as negative 103.7 kilojoules per mole. And like I said, even though we did it with enthalpy here, you could also do this with entropy values, doing the exact same process, doing the exact same types of manipulations. And that's how you use Hess's law to find overall enthalpies of reaction for these reaction mechanisms.